Lecture 4. In this lecture, which will be the concluding lecture of the Simple Harmonic Motion chapter, we will look at energy in simple harmonic motion, as well as the superposition of simple harmonic vibrations in one dimension. To investigate energy in simple harmonic motion, let's consider the case of a mass that is undergoing simple harmonic motion given by x of t under the action of some conservative force of that familiar form that we saw in Hooke's law. Now, this doesn't mean that there has to be an actual spring involved. I mean, I refer you to the example that the investigation we did on interatomic or to motion near equilibrium and interatomic forces in the first lecture on simple harmonic motion, as well as the homework tutorial problem on the two oxygen atoms. So we're not restricting ourselves here to mechanical block spring systems. It's important to note that. Okay, but we saw how we can calculate the potential energy in this case using a normal definition, where we get an expression which you might also have calculated by other means in first year. And the kinetic energy, of course, is simply given by this, the basic formula. So the total energy, in other words, is this expression. Now, as we saw, or rather realized in the first simple harmonic motion lecture, when the force is of that form, the differential equation that we derive comes to this, where we know what the general solution is, and that omega equal to square root of k over m represents the angular frequency. And now with this, we can massively simplify the expression for the total energy by simply substituting for x and its derivative from the general expression, and then run-of-the-mill simplifications, cancelling and grouping of terms. We reach this point with a familiar trig identity, and we are left with a nice clean expression for the total energy, where you will notice that that total energy is proportional to the square of the amplitude. So doubling the amplitude has the effect of quadrupling the energy. And this expression you can use in a similar way that you exploited total energy expressions to solve various mechanical problems in first year. In a similar way, you can use this expression to answer some of the problems in the homework or tutorial problems. And now we get to superposition of simple harmonic motion. Here we will look at the superposition of simple harmonic vibrations in one dimension in two cases. The first, the vibrations have equal frequency, but the amplitudes and or phase can be different. And our approach will be to use a phasor, which is just a vector representation of a vibrational wave, which will give us a geometric illustration of the story and give us a way to find the superposition of the two vibrations. Now, how it works is that the angle set by the phasor is simply that omega t plus phi term. It is the phase of the vibration or of the wave. In other words, it's the angle that gets fed to the cosine function. And the magnitude of the phasor vector, in other words, the length of the vector, that is just the amplitude of the vibration or wave. Now, this is something you might not realize, but you are already kind of very familiar with. This is essentially a repeat of uniform circular motion that we saw in the first lecture. There we had a blip going around in the circle, and the blip's shadow on the x-axis, or the projection onto the x-axis, that was what we refer to as the simple harmonic motion. And we saw that was given by x of t equal to a cosine omega t plus phi. Right? Our first introduction to simple harmonic motion 2 lectures ago. Now, the phasor setup here, as it's defined, as I defined it here, is essentially the same thing. The only difference is we're replacing that little blip that went around the circle, we're replacing it with a vector from the origin to the blip, from the origin pointing towards the blip. So that's all that changes. So in other words, we have this. We were used to a blip going around, but now it's just a vector going around. Okay, so what does this have to do with superposition? That's illustrated here on the right, where I've got two vibrations that I want to calculate the sum of superposition of. This red one and this blue one. And what this amounts to in the phasor approach is simply adding the phasor vector of the one vibration to the phasor vector of the other vibration, where the blue one's tail, I put at the head of a red one just to make it more obvious. Normally you would put it here, but not that that would make a difference to the sum. Okay, and then the sum of the two phasor vectors gives you the phasor vector of their superposition or their sum. And as you can see, that is just another vibration with the same form, but with a different amplitude and a different phase. And then you just have to calculate it. And to calculate it, you can see from the phasor approach that it is reduced to a vector algebra exercise, where you just have to use basic or intermediate geometry, yes, to just find the length of the sum of the two vectors, of the two phasor vectors, and its angle theta. Okay, so it's just a vector algebra problem where you use your knowledge of geometry. So in this case, just like in the previous page, we've got these two vibrations, and the sum of them is then just r cos omega t plus theta, and you use geometry and you can find, and this is a good exercise to see if you can manage it, find an expression for r and for theta. And now let's look at the case of two vibrations where the frequencies can be different, but we keep the amplitude of phase the same. So something like this, those two vibrations. What do we get if we calculate the superposition of those two? In other words, this sum. Well, let's substitute the terms. And then what is very interesting, and we'll explore this a bit, we get this if we go through a couple of steps. And this again, this is something I think you should go through. It is certainly much, much, much easier than the previous page's derivation. It just takes about 2 or 3 lines. And this is something that is surprisingly easy to explain, perhaps, and it's a nice illustration of how I think you should remember proofs in general, is by remembering their stories. And this one's story is pretty simple. It makes sense. Okay, so try to follow the following. Okay, first go and see what is the double angle formula for cosine. What is cosine of a plus b, and what is cosine of a minus b? Then see that both of those formulas will have a form. Let's say the two angles are alpha and beta. Cos of alpha plus beta and cos of alpha minus beta both have got a cos alpha cos beta form. But the one has got a plus sine alpha sine beta, and the other one has got a minus sine alpha sine beta term. And that is where the story starts, is by trying to use that property to play a dirty trick and to simplify the story. Now let's suppose that this angle is alpha and this angle is beta. And let's suppose that alpha is smaller than beta. What you're going to do is write down what is the middle point, the midpoint between alpha and beta. And then, of course, the distance from alpha to the midpoint will be the same as the distance from the midpoint to beta. Let's call that distance d. Then, to get from here to here, write this angle as the midpoint minus d, and this one as the midpoint plus d. And then use the double angle formula for cosine, and presto, you've got this form. Okay, so nice little short exercise that you can go and do. Okay, now we'll be less concerned with that derivation and be far more interested with what this actually means and how to interpret it. And we will illustrate that by exercise examples. Okay, so for exercise 6, we have to sketch those two components in the composition, in the superposition of the two vibrations, as well as the superposition itself. Okay, so I've drawn ahead a little bit here to save some time. Okay, so let's think first about these terms appearing here, omega 1 minus omega 2, or omega 1 plus minus omega 2 over 2. All right. Now we're going to discount the case where omega 1 and omega 2 is the same, because then this term is just 0 and this term is then just omega. Then it's the composition, the superposition is trivial. So one's going to be larger than the other. Doesn't matter which one. Because cos of x is equal to minus x, we could have here omega 2 minus omega 1. That doesn't matter. So let's suppose, omega 1 is greater than omega 2. So then if this is, say, your real line, and this is 0, then omega 1 is larger, so then let's say omega 2 is here, and omega 1 is here. Okay, so what is this term going to be? Omega 1 plus omega 2 over 2. That's just the average between the two. So there. Omega 1 plus omega 2 over 2. And this term, that's the difference between them divided by 2. So that's going to be here more or less. So omega 1 minus omega 2 over 2. Right, so clearly the one term will have the coefficient in front of the t will be smaller than the other term. So this term will always be smaller than that one for the purposes of the sketch. Okay, so remember what that means for a function like this. If we put something in front of the t, in front of the independent variable, and if it's smaller, then the graph is more stretched out. If it's bigger, then this graph is more compressed. Okay, so that's just first year calculus or high school work. So let's draw that one, and keeping in mind that value is smaller, so it's going to be more stretched out. So let's say something like this, for example. Something like that, and it continues. And what I sketched here was x equal to f of t, that one. All right, and now by comparison, this one has a larger coefficient in front of the independent variable, so this one is going to be more squeezed in. So to pronounce that effect, let's make it very squeezed in. So something like, well, it's going to be difficult to be very accurate here, so let's just, okay, this is tricky. Well, you get the idea. This is not very neat. Oh, okay, that's not very nice looking, but okay, we want to explain something, and this will suffice for that. All right, so this is very, look at that, that's horrible. All right, but anyway, this conveys the idea. Right, and now for h is the product of these two. So what's the product of these two going to look like? Okay, for that, just get a blank piece of paper somewhere. For that, suppose you have, well, note first of all that these two values are going to be between 1 and minus 1, both of them, of course. 1, minus 1, 1, minus 1. Okay, now, suppose you've got something of the form, something that looks like this. Well, let's recreate another cosine graph that's squeezed in between 1 and minus 1. So let's say you've got something else like this, very squeezed in. Okay, so this is a graph that's very squeezed in. So similar to, to g of t. And you have another graph. Let's say this is something that's also between 1 and minus 1. Let's suppose it's something like e to the minus x. So something that looks like this. Let's say this is f and this is g. What is f and the product of f and g going to look like? F of g. Not f of g, fg. Product of these two. Well, both of these functions are between 1 and minus 1. So what's going to happen if I multiply f with g is every single term, every single y value will be multiplied by something some value between 0 and 1. So you've got to think about it a little bit to see that what's going to happen, specifically if both are between 1 and minus 1, is that this one is going to be squeezed into this one. Well, this one will also be squeezed into that one, but that's a bit more difficult to try and think what that's going to look like. It's much easier to think what it's going to look like. This one gets squeezed into that one. So in other words, what it's going to look like is something like this. Let me just draw. So there is G, but it's going to be, so it's this, the product's going to look something like this. So going to be squeezed in like that. Okay, between 1 and minus 1. Right, so think about that a little bit until it makes sense. Okay, so what's going to happen here then? Both are between 1 and -1. So when I multiply these two with each other, this one is going to be squeezed into this one, or equivalently, this one is going to be squeezed into that one. Now, it's easier to think of what it's going to look like if this one gets squeezed into that one. So let me draw that. So I'm going to recreate that one a little bit. So something like that. And now the green one's going to be squeezed in between. All right, then what blue? Okay. So it's going to look something like this. All right, now again, this is difficult to do accurately, so it's going to look something like. You can make nice sketches like this in Sage Math or whatever program that you're using. Okay, so this is equal to g of t. So you see there what happens. I've got this one squeezed into that one, so I get these kind of these clumps almost that come out. The only difference is it's not going to be between 1 and -1. There's a 2a term in front. So this one is horizontal axis will be at 2a and -2a. Okay, now as I've drawn that, that's a little bit difficult to see. Let me, with the rockwood, give you a slightly better idea. So if I were to make this idea more pronounced, it would have looked like this. So I've got the one. So you get the idea. That's what it looks like. It's going to look better the higher the frequency of this inside function is, but that's difficult to draw by hand. Okay, right. Now what's significant about this? What is significant about this is that what we are seeing here are examples of how beats work. These are beats which you can hear. If these were sound waves, then you would hear these little beats coming out. So each of these little are beats. So this is a beat, this is another beat, and this is another beat, and so on. Now, what are the frequency of these beats? All right. Well, actually, we're done with the question now, but let's think about this a little bit more. What are the frequency of the beats? So beat frequency is equal to what? Well, you might say it's the frequency of this graph. Wouldn't you agree? That might make sense initially. But the time it takes for this red one, this f of t, to do one complete oscillation is from there, or let's start from here. It's from there to there in a horribly timed message. It's from there to there. That is one oscillation, one cycle of the f function. But in that time, we get 2 beats. So the beat frequency is going to be equal to twice the frequency of, well, how shall I rewrite this? Well, okay, frequency of f of t. Okay, so let's write that down. What is the frequency of f of t? All right, so that is standard. That is just omega 1 minus omega 2 over 2 times 1 over 2 pi. And what does this simplify as? Okay, 2's cancel. All that I'm left with is omega 1 over 2 pi minus omega 2 over 2 pi. And this is the frequency of the starting vibration function, the one of them, the one cosine of omega 1t, minus the frequency of cos of omega 2t. Good. Now that's quite fascinating. That means what that's telling us is, let's say you've got a fairly high frequency sound, like 1000 hertz, or let's say 500 well, what does it matter? 100 hertz, let's say. If you have 100 hertz and you've got another sound that is 101 hertz, then the beat frequency that you're going to be hearing is going to be 1 hertz. So if you play a 100 hertz song or tone on top of a 101 tone, then you're going to, over a 101 hertz tone, then you're going to hear 1 hertz beats. All right, now we're quickly going to do apply this in exercise 7, and then I'll play some examples of that happening so we can play around with it a little bit. Okay, so for exercise 7, we are told that an A string of a violin is a little too tightly stretched, and 4 beats per second are heard when the string is sounded together with a tuning fork that's oscillating accurately at concert A 440 Hz. Okay, what's the period of the violin string oscillation? Okay, so what's going on here is we're hearing beats at the frequency of 4 Hz, and it's due to overplaying or playing on top of each other or hearing on top of each other 440 Hz tone from the tuning fork and the unknown tone from the violin string. So we know the beat frequency is 4 Hz and the known frequency is of the fork, and that is 440 Hz. And because the beat frequency is 4 Hz, that means the difference, the absolute difference between the violin and the fork is 4 Hz. So thus, the violin is at, the frequency of the violin is either 444 Hz or 436 Hz. But it says it is too tightly stretched. So what happens if a string is, well, think for yourself, if you take a string, the harder you pull it, if you pluck it, it's going to increase the frequency at which it vibrates. So we can deduce from this, if it's too tightly stretched, then that's going to mean that the frequency of the violin is more than it should be, and what it should be is 440, so the frequency of the violin is more than the frequency of the fork, which is vibrating at the proper frequency. So thus the frequency of the violin is 444 Hz, as simple as that. All right, and now we can continue we will create some of our own beats to test it. Right, so here I have opened a program called Audacity. It is a fairly, or perhaps, or I think a very well-known audio editing program, which will allow us to listen to beats. Okay, so let's generate a 440 Hz tone for 15 seconds. So that will sound like this. As you can see, it's just a normal sine graph or cosine graph, 440 Hz. And now let's generate another one. And let's make this 441 Hz. Okay. Now, according to what we just saw, because there's 1 Hz difference between them, we should hear 1 Hz beat. So beats at the frequency at the rate of 1 per second. Okay, so let's listen. You hear that? Right, and you can time that. Those are on the second. Let's change it. Let's take this one out. Wait. Yes. Okay, good. Okay. Let me just reset it. Oh, right. And let's generate another one. Okay, so how about 440? 442. Okay. So now the difference is. No, I've overwritten it. Okay. Now I want generate 442. There we go. Right. Okay. Now it's a 2 Hz difference between the two. They both look pretty much exactly the same. by 2 Hertz difference. So what do we expect to hear? We expect to hear a beat frequency of 2 Hertz. So that would be 2 beats every second. Let's see if that is what we indeed hear. Okay, see, that's how beats work. Okay, how about, let's play a little bit more. Let's add, how about 40.5. Now there's a half hertz difference between them. So now the beat frequency, so now they're very close. And now the beat frequency is going to be half a hertz. So half of the oscillation in a second. So it'll take 2 seconds to hear one. So 1 beat every 2 seconds. Let's see if that is what we hear. You see, exactly as we expect, straight from the mathematics. Okay, now you can play around a bit more. Oh yes, it doesn't actually matter, of course, and this was reflected in mathematics. It doesn't matter if the other one is 441 or that's what we already heard. Let's make it 39. That should have no effect. The difference is still 1 Hertz. Yeah. Okay, let's start here then. See, it's still exactly the same thing. So unfortunately, just listening to the beats doesn't tell us whether the unknown, if the one is higher or lower than the other one. That we can't tell. We would have to be able to tell that by other means. Okay. What else can we do? Let's make it much higher. So we've got a 440. So let's make a 440. Let's make it even a 450. So that's 20 Hertz. Sure. I don't know. It's kind of so. No. I meant 60. Okay, so now it's 20 Hertz difference between the two. So that should mean beats at the 20 Hertz. What's that going to sound like? Yay, all right, cool. All right, this is, so if you have a frequency source that you know exactly what the frequency is, then I mean you can do this to tune another instrument, which is why I think there used to be like telephone numbers you could call, listen to a specific frequency and then tune an instrument. Well, okay, I don't want to continue playing with this too long, but you can certainly install the software and play with it yourself. That's 450, so that should be 10 Hertz. Yeah, I think I heard that in the movie sometime. All right. Okay, and some of the more observant among you might have thought what its effect going to be of changing the amplitude. Okay, let's make another one. 50. Let's go back to 441. 442. Why not? And we should still hear beats. They're going to sound a little bit different, but I don't think it's going to be distinguishable. But the amplitude does play somewhat of a role, so I invite you to go and look at the mathematical expression and think a little bit about what effect it's going to have if the amplitudes are different, and see what you can conclude from that, or what you can theorize. Okay, but feel free to go look for this free software and install it and play around with it, and then you'll have a very good idea about how beats work. Okay, but anyway, that is it for this, the concluding lecture on the Simple Harmonic Motion chapter.